and there is essentially an epsilon to the minus d here. The small d is the dimension of M. So maybe I should have remarked that again in this picture. The space, the Y space, is capital D dimensional. The dimension of the manifold is small d, much smaller than the ambient dimension, capital D. And there will be almost only small d's in here. In particular here, the number of points that you need to have in your database today, the training data set, depends crucially on the accuracy and on small d. Then, this is your database today, samples from a probability measure, let me call it capital Pi. And these samples are all in that tube around a smooth manifold M. Then I'm going to give you an algorithm that, given your training data set today, it constructs a set of vectors. I'm going to call it phi at epsilon. It constructs and it gives to you a nonlinear encoding operator, d hat, and an inverse for d hat, that have the following property. So these were the ingredients in the dictionary learning problem. A bunch of vectors, an encoding map. So before, in the standard dictionary learning procedure, this was the encoding map. You have a bunch of vectors and you solve this minimization problem. I'm going to give you a completely, that's a nonlinear map. I'm going to give you another encoding mechanism, a nonlinear map, and an inverse. What can I tell you about the dictionary? Well, I can tell you how large it is. That's what we called M before. So the cardinality of the dictionary is epsilon to the minus d over 2. No larger than that, but typically as large as that. I want to tell you how sparse the encoding is. It's d plus 1 sparse. The manifold is d-dimensional. The sparsity that we get is d plus 1. The reconstruction error is no more than epsilon. That's the parameter that you gave me. And I told you, if the training set is large enough, I'm going to get that accuracy. And I'm going to get it not on your samples today, but forever. No matter which samples you have from your probability measure, when you encode the data with my encoding algorithm and you reconstruct, you get accuracy epsilon. Guaranteed. So this, I claim, essentially solves the dictionary problem in this case because I can tell you exactly the relationships between the size of a dictionary, the sparsity of a representation, and the approximation error. And all of this holds as soon as the training set that you have is large enough as a function of the accuracy that you ask and the intrinsic dimension. Now, your training data set is random. So the dictionaries, the algorithm runs on that. So the dictionary is random with the data. The encoding map is random with the data, and so is the decoding. So actually all these statements are true, not always, but with very high probability. It could happen that you're so unlucky that you sample the same point n times. That's very unlikely to happen, but if that happens, I'm not going to be able to learn a good dictionary. So there is a set of events which are very unlucky, for which I'm not going to learn a good dictionary. But with the overwhelming probability, the algorithm will construct a good dictionary in this sense. This would be a very concrete algorithm. So, and these guarantees are exactly on the output of the algorithm run on this training data. So I should tell you how long the algorithm takes to run. The running time is here for the construction of phi, the dictionary. So you should focus on this term, which by the way is wrong. Sorry, it's d over 2, not 2 over d. So this is essentially n. Okay? So the algorithm runs in times proportional to n. With the constant here, this is a constant, like 3 or 4, to the intrinsic dimension. So it's exponential in the intrinsic dimension. So this constant is not good if the intrinsic dimension is large. And then there is another constant, which is simply linear in the ambient dimension. After all, I'm going to read in the data that is size d, capital D times n. And it's quadratic in the intrinsic dimension. So the algorithm is, I can promise you, it's fast. It runs linearly in the size of the data, and quadratic in the intrinsic dimension with a constant which is exponential in the intrinsic dimension. The encoding map is super fast. It's intrinsic dimension times ambient dimension, essentially. And the encoding and the decoding is even faster than that. And these are not iterative algorithms, so there is nothing hidden in those big O's and so on. All the dependencies on the crucial parameters are exactly there. Any questions about this theorem? By the way, this appeared a couple of months ago on the archive. It's submitted to GMRA, I believe. And it's joint work with Nate Strawn at Duke and University of Maryland and perhaps John Hopkins now, and Stas Minsky at Duke.
The width
yes.
of the tube tube is small. You said small. But how small?
Well, so that's in the nature of the data. So it could be the size of a noise, and since we work at a larger scale, then we're not doing denoising. We're going to approximate the data at the level of noise. Or it could be that the manifold model was really bad. The data was really complicated and far from being a manifold, and so we are not able to cope with that. And so the tube might be large because of that. The results that we get from multiscale SVD that I talked about yesterday suggest that oftentimes these tubes are pretty small. And because what we're measuring with that algorithm is actually exactly something like this sigma.
So works.
Regardless. So sigma is sort of given. It's the level of noise or the size of this tube that you measure somehow, for example, by running multiscale SVD. But the algorithm then, provided that you don't ask to denoise or to do something clever inside the tube, it's going to have these guarantees.
Now, when you say that you take the samples IID, now in practice, in a practical algorithm, right,
yes.
you need to use pseudo random.
Well, so the way, so IID, so identically and independent. So there is one probability measure, say on patches of natural images, and I'm drawing independently from there. Well, for example, you may say in the field experiment, that's not necessarily true because you take this picture and then you take all the patches in that picture. Are you going to call those independent? Well, maybe they're far away, but not even really, right? If it's a picture of a tree, those are dependent in some way. They're certainly more dependent from each other than they are if you took a patch from an image of a tree and an image of a building, for example. So independence is often very hard to guarantee. In the case of handwritten digits, well, different people drew their digits, so there is a good amount of independence. Independence, I don't believe, is really crucial. You could replace this, and this is sort of standard machining probability, by not very strongly dependent, and then you will get, but that you will need to quantify that. There are ways of quantifying that. So, for example, the correlation between the samples decreases sufficiently as you see them. And then the results would also hold with high probability, but I didn't write down what the probability is. We know exactly what it is. But the probability then would have this decorrelation factor in there. And now I could ask, how do you know that decorrelation factor? But if you had some knowledge of that, then the result would be a little bit more, would be applicable. We have not written down such a result, but very standard machine that replaces independence with these things. Yes. Yes.
Still on the structure of the probability density or
yes.
distribution. Do you require for the performance of the algorithm to be good that the probability distribution has I don't know, higher moments like 2 moments, 3 moments? Or it
yes.
can be a very
Great. Okay. So I didn't want to make the talk that technical, but so the manifold is compact, so everything is bounded here. So you got all the moments that you want, because we also assume that so first of all, everything is bounded, and second, we assume that this probability measure is absolutely continuous.
Along the direction of the tube also. I mean, the tube is finite.
The tube is finite, but also the whole tube and the whole manifold are in a box. Okay, everything is bounded. Which, by the way, I don't think is needed because, if you have a probability density, it decays at a certain point. So if it was not bounded, given n samples, you truncate at the right level, and then it's bounded with, and so on. But also we assume that the probability measure pi is absolutely continuous with respect to the Lebesgue measure in the tube. So it doesn't blow up, it doesn't do anything odd inside the tube. And the paper actually keeps track of all the constants, and it gives you all the constants which appear, in here. That's due to my co-authors. You can write this statement in a more, statisticians usually don't think in terms of fixing accuracy and getting everything else as a function of accuracy, which is how I like to think, or how people that do numerical stuff like to think. But in terms of they think in how everything depends on sample size. So you can rewrite everything in terms of that. And the result will look like this. It will say that in the future, when you collect data in the future, X comes from the probability measure, possibly in the future. You encode and you decode. The error that you're going to make with very high probability decays like n to the minus 2 over d plus 2. So the more samples you have in your training data, that's n, the better you will be doing in the future, all right, at this rate. And note that in this rate, you have n to the minus something divided by d, and that's a manifestation of a curse of dimensionality. The larger d is, the more samples you need and exponentially more you need, but it's a curse of intrinsic dimensionality. There is no capital D here. There was no capital D anywhere here except down here when we're actually reading the data. We look at all the data, so we're reading the matrix. But there is no capital D in the number of samples, in the accuracy, in the sparsity, nowhere. All right? And you can ask whether this rate is good or not. We believe it's optimal, but we have not proven it in the sense that there is no other way of encoding this type of data any better than this. And the reason for such a bolsterous claim is that the way we do this is not too unlike the problem of doing manifold learning. It's not the same problem, but it's related. And the best possible rate for manifold learning has been shown to be this by Wasserman and collaborators. And so we think that the rate is optimum. It's certainly better than any dictionary learning algorithm that is out there. And the algorithms are also the fastest out there. So now I wanted to tell you how we do this. All right. So the construction is very simple. So, and this is all the work with Bill Allard and Guangran Chen. It's something that we call geometric multi-resolution analysis. It's sort of how to do wavelet analysis, but not for a function, but for a point cloud in high dimensions. And so we have data in high dimensions, in that cube, for example. We're going to divide the data in a hierarchical fashion. So we're going to divide the data into pieces, which I call CJK. J is going to be for scale, and K is just going to index the pieces as scale J. And these pieces are hierarchically organized. So we construct a tree. At every node, we have a CJK. At the top, the node is simply the whole data set. And the data set gets split into pieces. 2 here, just to make my life easier in this picture. And at each node, there is a subset of the data now. These 2 subsets at this scale are disjoint, and the union is the whole data. And then each piece is recursively split. And if you fix a scale J, the pieces at scale J are disjoint, and the union is the whole data. Think of these as dyadic cubes of sorts. Then in each of the pieces, we're going to do the simplest possible dimension reduction method, which is PCA. PCA, as we saw yesterday and as I mentioned today, makes a very simplistic assumption that the data can be approximated by one plane. Well, I'm going to make that assumption not for the whole data, but at in pieces of the data. So in each piece of the data, I'm going to compute the covariance matrix, and I'm going to find a low-rank projection by doing PCA. So I'm going to construct vectors, which I call phi jk. Those are like the U vectors in the second slide, that project my data locally onto a low-dimensional plane. And the dimension of the plane is going to be small d, the target dimension of the manifold. So at each node of a tree, there was a subset, CJK. But at each node of a tree now, I'm going to put a bunch of vectors, an orthonormal basis for a low-dimensional subspace spanned by phi jk or phi jx. But now, at this node, I have a low-dimensional plane, and at this node, I have a low-dimensional plane. Are they different? Well, you can think that you're sort of zooming into your data, you're getting smaller and smaller pieces, and you approximate each of the pieces by a plane. If there is any regularity in the data, these planes are not going to rotate very much as you zoom in. So what I could try to do is encode the difference between these 2 planes. And there is a way of saying mathematically what it means to encode the difference of 2 planes. And that's what we do. That's the last step. In the last step, we encode the difference between a farther plane and a child plane. And so I think of the difference sort of as lying on this edge. It turns out that you can do that by constructing a low-dimensional plane again, such that all the differences between projecting a point on this plane and projecting a point on that plane are encoded accurately by a low-dimensional plane, which I think of as being spanned by wavelets. These planes I think of as scaling functions, and these are like encoding the details of the differences, like wavelets. So if you have a point now in high dimensions, you can project it onto the plane that is closest to it. Once you have that projection, you can write the projected point as at that projected point projected onto the farther plane plus a correction onto the wavelets. And then you can write the projected point as a projected point plus a difference. And so you get an expansion on every point in high dimensions as a sum of its projection onto the root plane at the root plus a correction, plus a correction, plus a correction.
In which
That's,
dimension,
yes.
each element, you start from the dimension big D, right?
Big D. And then immediately, remember that the points were actually close to a D-dimensional manifold. So immediately I decide, oh, my point in capital D dimension is actually close to this little plane that I constructed here.
And now this is a lower dimensional space.
Now this plane is a lower dimensional plane, it's small d dimensional, and I've projected my point, and I've approximated it.